Alright, let's look at today's Leetcoding challenge question. Longest common subsequence. We have two strings, T1 and T2. We need to return the length of their longest common subsequence. So the subsequence of the string is the string with some removal, but still retain the relatively ordering of the characters. So delete only, no rearrangement. A common subsequence of the two strings is the subsequence that is common to both. So we can do this deletion from both of the strings with minimum number, I guess, so that the remainder of both strings can be the same. And we want to find the longest of such a subsequence. So this is a really classic dynamic programming question. And yeah, let's look at some examples. We have A, B, C, D, E, and A, C, E. We drop B and D, we can get ACE, so we return the length of that, which is 3. The second example, both input are the same, so we return the length. The third example, there are not even a character shared in between, so the answer is easily 0. Alright, so let's look at this question. Let's just call this function LCS for short. So this question is asking us the LCS between these two strings, which is equivalent to slicing these two strings towards the end from the beginning. Then when we try to think about how we rely on some kind of previous calculated result to help us to reach towards the end of getting really this thing, what if that we know the result of finding the longest common subsequence between the two strings up until the very last character? If we know that number, it's gonna be that plus 1 if the very last character are the same. What if let me actually just make it more. What if the very last character are not the same? What do we do? That's essentially going to be we give up on that match, right? So we can choose to choose between two options. One is to shift the L1 by the T1 by 1, or we can shift the T2 by 1, and just gonna find the longest common subsequence between those. So it's gonna be the maximum between two things. This is trying to find the longest common subsequence between the first string towards the end and the second string towards the last but one, or the alternative where we use up all of string 2, but for string 1 we leave that very last character out. That's the case when we couldn't match those end tail characters of those two two strings. Since that we couldn't do this matching, we just pick whatever that's maximum by allowing the string shifted by 1. This pretty much just gives us the recursive relationship for this. We're just gonna memorize the intermediate result. There's one thing. So this is pretty much the transition formula for recursive calls. And the base case is if the both string are 0, so that's gonna just be 0. Yeah, because there is nothing to match, so they should be 0. Okay, so yeah, that's the base case. I think I'm gonna change the notation a little bit because this is treating that we're putting one string, physical string in here, but what we really need is just that indices. So in the code I'm just gonna use indices, but for demonstration purpose I guess this makes more sense because It's physically calling the function on the string that's shorter to the certain length. Just gonna be lazy and write a recursive method first and top-down version first, and then gonna go back to code up the bottom-up version, which is always preferred. Just get the length of the two strings, and I'm gonna just be sloppy today. Instead of writing a hash map or array to cache those results, I'm just gonna use LRU cache here. Oh, so this is the base case is 0 is not included, so that's this kind of brackets rather than the so this kind of parentheses. So that translates to this line here. So this means that we are matching an empty string with some other stuff. Whether the other one is empty string or not, the result is always going to be 0 since that one of the string is empty. Otherwise, we're just going to translate this relationship back into the code. That's T1 i's location is equal to the j's location from the second the alternative string. Then we're just going to grab the maximum alignment between the two strings with length -1. Oh, I have a typo up there. Otherwise, just gonna take the maximum between the alignments with one character shifted from either of the strings. This is return here. Oh, sorry. I'm being too sloppy today. So it's for this function call, I'm just pathing the indices, not the slice of the strings. So in the end, we're just gonna call this function to march until the end. Yeah, this should be it. Let's see if it works. Does it work? Okay. Let's put more example. Looks right. Yeah, so the time complexity for this is going to be the L1 multiplied by L2. So since the only options that you can have here is the combination between 0 towards L1 and 0 towards L2. So from -1 to L1 -1, that's the possible ranges for I. The J is going to be -1 towards L2 -1, so the total possibilities of calling this function is going to be those two multiplied together. So that's a linear order of length of those two strings multiplied together. That's for the time complexity. For the string, we're going to cache results of this function call for however many input signatures that we can have for the LRU cache to store that. So it's going to be the same order of m multiplied by n. Let's see. Yeah, it's working. So this is a top-down memorization lazy implementation of a top-down memoization method. We're gonna then translate it into a bottom-down version. So instead of doing this, we're gonna physically create a DP table, which is gonna be the pretty much the I and J, all the combinations for that. For easy of handling base cases, we're gonna pad one row and one column in the 2D version of the DP table to be 0 to cover all the base cases. So we're gonna create the table. So yeah. So the DP IJ, it's pretty much just gonna be LCS IJ. We're basically just physically storing all those information, and instead of recursively building up the table, calculating those methods, we're gonna fill up the table. And then it's just this logic here. Since we padded 0 to the 0's column and the row, the IJ will be enumerating from 1 towards the L1. So the getting that location, getting that text, the character is going to be using this index -1. So in the end, we just return the bottom right element, which represents the LCS between the two strings marching towards the end of both. So this is the bottom-up version. We have a for loop. So by looking at this, the time and space complexity is quite obvious. This is for the space. We have the two multiplied together, and time is this. So if it's working. Okay, let's see. Yeah, this is accepted as well. So a final improvement on this is that we noticed that the recursive relationship here, it only depends on I-1 or J-1. So it never would actually require us to go towards a couple of columns, a couple of rows in above. So we can actually depends on whether we want to save on row or column. We can reduce this to a one-dimensional DP, and for that we actually would want I guess we'll do that later. So we will first convert this to one-dimensional. Maybe we just keep rows, rows, and then we'll do some treatment to the two input string to make that row to be as small as possible. So the looping is still the same because it's essentially the same question, except that what we need is the two adjacent rows. We will never need the full table. When we process the ice row, we can discard the I minus 2. So we're only working with 2 adjacent rows. And after we're processing that, we're just gonna assign this new row to be the old row. So what do we do? It's the same thing here. Just so it's the new DP table. New row is going to be 1 plus the old j's value. It's old j minus 1, I'm sorry. Otherwise, it's going to be the previous row and the current row, but the previous column. So that's ndp j minus 1 and dp j. So that's pretty much it. And as a result, in the end, we just return the last element of that one-dimensional DP table. For this, we would want L2 to be as short as possible. So we'll just do, we want the T2 to be as small as possible. So it's T2, T1 equal to sorted T1, T2. T is just the length, so we're gonna swap the T1 and T2 to make the smaller one to be T2, so that the DP table only depends on the length of that one, so it becomes shorter in terms of memory. So it's gonna be the minimum between the two lengths. The time complexity is still the same. We have essentially the double loop here, but the space is gonna be linear with respect to the shorter string. Does it work? Okay. So this is this is pretty much this question. Just think about this matching towards the end. Or try to relax that a little bit to try to think about what if we match towards certain location and we want to expand beyond that. What's kind of the relationship there? What's kind of the scenario there? If we can match the 2 locations we want to match from those 2 strings, what we do is take the 1 plus the previous matching result. Otherwise, we're just gonna do a 1 shift because we couldn't match. We pretty much have to give up on one of the characters, either from string 1 or from string 2. So this is the recursive relationship here, and the baseline is simple because matching empty string to anything is basically 0. So we can either do top-down memorization or we can do bottom-up. And when we do bottom-up, looking at the relationship there, we will never really need anything that's 2 rows or 2 columns beyond what we're currently working on. So we can do a little bit optimization on space. So that's the question for today.